So what I now do is I move the tip to the opposite corner. Oh, wrong zoom. And that defines the square area where the scan needs to take place. So I need to define these two areas. And then when it's set, it will do a measurement, send an RSA for each position, do the measurement, and then make a plot out of it to show the relative strength. And I'll set it to 15 by 15. And then I'll go on with the talk, and at the end, hopefully there's a nice picture. And now it's moving back. Oops. Of course, more demo effects. For some reason, it doesn't see anything on my... Yeah. Finally, no. They always tell me make movies, don't do demos. Now I know why. Another bug. Okay, I'm going to quit the demo here. I already arranged that I can do more demos in the afternoon in a tent. I'll explain later where it is. Is this visible? Yep. So basically what happens is this. So you see it will move around the thing on the edge. Turns around. The tip of the probe is floating just above the silicon package. What we found is that it isn't necessary to open up and decap the package. So the millimeter or so distance between the real die surface and the probe doesn't influence the signal strength that much anymore that it's necessary to do this. What you see here is the trigger signal. And this is a small wire connected to the LED pin that supplies the trigger for the oscilloscope. And then on the screen, yeah. So this is the plot that you get. So what you see there is the blue and the red and the yellow. What is calculated is the spectral intensity of the signal. So this is doing an FFT and creating a single value of the intensity of the signal. And by using a few sliders, you can choose the frequency bands to get a picture above the chip. And actually, what it looks like is this. So this is what you already saw. And here are the sliders I told you about. What you can see is that there are clearly areas that are more active than other areas. What happens if I slide is that actually it jumps around quite a bit. And now you see actually a square area that seems to pop up or actually pop down in this case. Anyone an idea what that is? Sorry? I cannot fully hear it, but the die, yeah, okay. Yeah, so you see bond wires and you see where the die is placed because the die itself actually doesn't emit that much EM. Now it distorts because the rest is so strong, it seems like there's no signal over the die, but there is signal over the die. The question is, what is the interesting signal? So bond wires may convert or transport interesting information like keys or stuff like that, but then you can also sniff them on the chip pins. For a real secure processor, actually everything that's interesting happens on the die. So you need to set your limits of your scan to only that area in the middle, and then it will show you where the areas are that are active. And actually, I think by setting certain limits, you'll see that there are, well, fakely there's an area here that's active. If I click on these areas, you can also see in the trace, now remove this, that the patterns are also really changing. In this chip, which is pretty simple chip still, you see that there's a basic pattern everywhere, but if you've got more complex CPUs, you'll see that the basic pattern is actually changing quite a bit, and there's only a few areas where you see a clear pattern. I saw a finger going up. Okay, the frequency for measuring depends on two things. The length of the operation you want to measure, and can you fit it in at the frequency you're measuring at, so what's your buffer size. But generally you want to be quite a bit over the frequencies that you're interested in. So the LaCroix that we use is 10 gigasamples, and we use the full 10 gigasamples for anything like at 300 megahertz. So we tend to try to go as fast as we can. But for RSA, for instance, this is RSA, it's a very slow process in software. So actually this is measured at 25 megahertz while the CPU is running at 57. So, and you can go much lower and still get the bits up.
Is there a rule to say, for example, 5 times CPU speed or something?
We use about 10 times the cutoff frequency of your low pass. And the low pass determines, for instance, just above the core frequency of the chip. And then our rule of thumb is about 10 times faster if we can.
Okay. But what about buffers? For example, we have a highly expensive oscilloscope that really is able to take 10 gigahertz, and you need really expensive memory to store maybe 1 second of acquisition.
Yeah, but in the end, the things we are interested in are mostly hardware crypto cores, and they are very fast. So we have very few situations where we want to measure really long. And also, if you then have to do processing, you don't want to have too much data. So most of the work in SideChannel is compressing the data. How can I keep the interesting stuff and get rid of as much of the noisy stuff? So resampling techniques and filtering techniques are important to try and reduce the data. Okay, I saw a sign that I need to hurry up, so let's try and do that. Yeah, some practical encounters. So we were looking at the Xbox and thinking, well, maybe power measurements. This is the power entry of the Xbox CPU. It's a complete flap of copper on the PCB. I think several tenths of amperes are going in over 3 lines, so there's not even a single point in the PCB that you can intersect and measure the power on. So actually power measurement is quite a challenge. And then if you want to use EM, the chip is beneath that power, beneath that heatsink. And if you take it off, the chip dies. So actually it seems all nice, but in practical situation, you can still encounter quite a few difficulties. Another one is, this is a Beagle board with an OMAP chip. The new packaging techniques shown above. You have the CPU underneath, and then a memory chip with 2 dies on top of the package, and it's all soldered together. So now, if you put your EM probe above, it sees the memory chip instead of the CPU. And here you see the power distribution chip, which is tightly coupled with the CPU. So you need to somehow figure out where to measure your power. So actually, again, in practice, you will encounter quite a few more difficulties. Okay, so this is about all the difficulties and all the pros and cons. Wrapping up, what does it mean for a product? Basically,